Okay, so for this video, we're going to talk about rolling motion and vectors. Okay, so let's start with rolling motion. Okay, so the basic idea for rolling motion is that it's to understand it as a combination of translational motion and rotational motion. Okay, so to see the difference, translational motion is when the center of mass is actually moving in a trajectory, typically a straight line trajectory. And the important thing here is that there's nothing about the object that's rotating at all. But in rotational motion, uh, all the particles that are contained within that object are rotating or moving around a fixed point. Okay? And to understand it better, typically that fixed point is within the object itself. Okay? And then in terms of the center of mass, the center of mass stays in a relatively fixed distance from that rotation point. So in other words, the center of mass is moving in a circular trajectory around that fixed axis. So the overall displacement of the center of mass is always zero. So for translational motion, if you just imagine a circular object like a wheel, for example, the translational motion of the wheel would be that the wheel is not spinning. So maybe it's a frictionless surface, but the center of mass of the wheel is moving with a velocity. And then rotational motion would be if we took that same wheel, but we took it off the ground and we held the rotational axis fixed, and then we let it kind of just rotate around that fixed point. Okay, so to get an object to roll, it's a combination of these two ideas. Okay, so let's look at what I mean by that, by combining these concepts of translational and rotational motion. Okay, so the first thing we need to understand is there's a very big constraint when we say that something is rolling without slipping. Okay, so the rolling constraint, which you already know, is that the velocity of the center of mass is equal to the radius of the object times its angular speed. Okay, and that's only valid if there's no slipping. So here we have, we'll just draw a wheel. Now, these aren't the same size, but just pretend they are. Okay, and so what we're doing is we're going to look at the two types of motion, translational and rotational, and show how these combine to form a rolling object. Okay, so the first wheel is translational, and we're going to add that to the rotational wheel, and the result is rolling. So let's look at what's happening. So again, the translational motion says the center of mass is moving with a speed v, but since there is no rotation, every part of this wheel is moving with the same speed. Now, for the rotational motion, every part is rotating with an angular speed omega. And if we look at the very top, that angular speed is the radius times the angular speed to the right. And if we look at the bottom, it would have an angular speed, or a linear speed, a tangential speed of r times angular speed to the left. And the center of mass is not moving, so its velocity is just v, because it's a fixed axis. Now, if we add across all these points, okay, so if we add across the top, you get v plus the rw, and since rw is the same as v, that means that the top of the wheel is moving with a speed twice the center of mass speed. Okay, and then if we look at the center of mass, if we add those together, you get v plus 0. And so v plus 0 is just v. The center of mass is just moving with the speed v. But then, if you look at the bottom, you've got v minus rw because they're going against each other. And so that result comes out to 0. So what that means is, in rolling motion, the part of the wheel, or the object, that is in contact with the surface is always instantaneously at rest. And this is what causes it to roll. The friction stops it from rotating on the bottom part of the wheel, which causes the top part of the wheel to actually rotate forward, which then is what pulls the center of mass forward, and that's how you get rolling motion. Okay, and then the center of mass has a speed VCM, and the topmost edge is always twice that speed. Okay, and so these are the ideas of what goes into rolling motion. So let's put some application to that. And the first place we're going to look is in energy. Okay, because when you think about it, and the energy of a moving object was always the kinetic energy. But if it's rotating as well, then that means you also have a rotational kinetic energy. So that, in combination with translational motion, is what we're going to focus here. Because if you think about it, we did a problem in the last video where because it rotates, it has two types of energies. But what if we do something like this? What if we put the wheel or the disc on top of a hill? Okay, so we're going to say that this is a sphere, and we know that conservation of energy tells us the total mechanical energy before and after are the same. And we know that because it's rolling, it has both translational and rotational kinetic energies. And of course, potential energy is just that of the height of the ramp. Okay, so if we go through this and simplify, let's say the object starts at rest. Okay, and we said it was a ball and it's not slipping. And so in the book, we get the moment of inertia for the ball, which is 2/5 mr squared. So we're just going to go through this and try to solve for how fast the object's going to move when it reaches the bottom. Okay, so with no slipping, that means we can use the rolling constraint. If it was starting at rest, we know the initial speed is 0. We know the initial angular speed is 0. And we know that the final height is 0 as well. So if we put all those factors into our conservation of energy equation, we simply get that all the potential energy we start with converts into two types of kinetic energy, a translational and a rotational. And so now all we need to do is plug in some expressions and start simplifying. So I can plug in I, and I can plug in with the rolling constraint, V over R for omega. And if I expand this out, 1/2 plus times 2/5 is going to be 1/5, and then the R's are going to cancel. And now on the right side, I've got like terms, so I can simply combine those. I can also divide out the masses. So we got 1/2 v squared plus 1/5 v squared. But when we combine those, that's going to give us 7/10 v squared. And so we divide over the 7/10 and we get the square root of 10 over 7 times gravity times height. So that would be the velocity of the center of mass as it reaches the bottom of the ramp. Okay? It's not a complicated idea, but that's how you would pretty much put it all together. Now, let's look at vectors in rotation. Okay, I know I went through the energy part really quick, so if you have to, pause the video and rewind it and kind of reflect on that. Okay, so when we talk about rotational motion, vectors are always we have to think of 3 dimensions. So rather than drawing the images out here, the book has some pretty good ones. So if you need to, check pages 317 and 318 to see the 3-dimensional images. You're also going to see something in there about the right-hand rule. And the right-hand rule allows us to use our right hand to visualize vectors. Okay, so the first vector thing we're going to talk about is this idea of a cross product. So if we're going to draw out in 3-dimensional x, y, and z system, think of if you're holding your hand, your right hand out, point your fingers towards your computer screen. So the direction of your fingers represents the x-axis, positive x-axis. Your palm will represent the positive y-axis, and your thumb represents the z-axis. So with that, let's do a cross product between 2 vectors a and b, and let's say they make a vector d. If I'm crossing a into b, let a be your fingers and b be the palm. When I wrap my fingers into my palm, my thumb goes up. So the resulting vector will point in the positive z direction. Now if I were to go the other way, if I were to take b and cross it into a, then I would have b pointing forward which would be my fingers, okay, and then A would still be pointing to the right now. And when I wrap my fingers into my palm, the resulting vector points down. And that's what we talk about when we say that a cross product is always in 3 dimensions. Now, some properties you're going to want to know is an x direction crossed with a y direction always produces a z direction. A y crossed with a z will always produce an x, and a z crossed with an x will always produce a y. And you can do this with the right-hand rule. And if you flip these, then you get the same result but negative. Okay, and then another important concept to know is that if you try to take a vector and cross it with itself, like x crossed with x, you'll always get 0. Okay, parallel components do not produce a cross product. Okay, so let's do an example of how to calculate the cross product. So I'm going to create 2 vectors, say vector A and B, and they all have just arbitrary x, y, z components. Okay, and if I'm going to calculate the cross product, what we need to do is we use what's called a matrix. You may have seen one of these in your math class, you may not. But we essentially set up a matrix and we determine the determinant of that matrix. So here's how this works. So this new vector C, we simply make a matrix. So you start with just 2 bars, and then on the top row I list my x, y, z components, the I, j, k's. In the next row I list all of the corresponding A components. And then in the next row I do all the B components. So notice all the x's are lined up vertically, the y's are lined up vertically, and the z's are lined up vertically. Now to do the cross product, you're going to set up this basic formula. You start with the I component, and there's going to be stuff, and then you subtract the j component. Okay, and this is important. Notice the signs alternate, right? You go from a positive I to a negative j to a positive k. Okay, now let me show you how to fill in the parentheses. So if we're going to start with the I component, notice what I do. I basically cross out the I column and row. And when you ignore those, you see 4 terms that are left. And what I do is I cross multiply them. I do AY times BZ. Then I subtract, crossing the other way, BY times AZ. Okay, now what's interesting is you'll notice we're looking for the x component of our cross product, and there's not a single x component in the work that's done for it. Okay, so that's kind of how you know you're doing it right. Now, I'm going to erase these marks on my matrix because we're going to do this again for j. And you can see it's going to get messy. So if you're writing on the same matrix, just try to visualize what's going on. So for j, I'm going to cross out the j column and the j row. And what's left is I can cross multiply ax to bz and then subtract the other way. It'd be az times bx. Okay, let me erase the marks on the matrix now, because now we're going to do it for the k component, the z direction. So I cross out the row and column for k, and then I cross multiply, I drew that arrow too far, so it's ax times by, and then it would be ay times bx. And so this would represent the entire work that goes into finding the cross product. And again, to help understand if you did it right, look at what component you're looking for. So like I'm looking for the y component j, there's no y components within that work. When I'm looking for the z component, there are no z components in that set of parentheses. So that's kind of a giveaway to help you know whether or not you're doing this right. Okay, so let's just do a quick example. Now, you won't really be given vectors that are 3 dimensions in length for the AP exam, but it's good to just kind of know how to set this up. So let's say that the A vector is just 3 in the I hat and B vector is 6 in the J hat. Now, you still have to write this in 3 dimensions. The difference is that since there's no K components, I'm going to fill in all the blank spaces with zeros. Okay, and now we do the same thing. It's I times something. So we're going to start by crossing out the row and column for I. And when you cross multiply it, you're going to see 0 times 0 and 6 times 0. Okay, then we're going to do minus the j component. Okay, so I cross out the row and column for J. We've got 3 times 0 and 0 times 0. Okay, and then we do the same thing for the Z component. So I cross out the K row and column. And then I cross multiply, I'll get 3 times 6 minus 0 times 0. Now as I work through every piece in these parentheses, you'll see that it's nothing in the I hat, nothing in the J hat, and 18 in the Z direction. And that should make sense because when you look back at the properties, when you cross an I with a J, it ends up with K. So the resultant vector was 18 in the Z direction. Now we're going to start this idea of cross products with torques, because torques are actually cross products. So if I give you, let's say that the R vector is negative 3I plus 4J, and the force vector is just, I don't know, 6 newtons in the K direction. So how much torque is felt about the origin given these vectors? Okay, so torque is the cross product of R and F, and the order again matters because if you flip the order, you get the negative of that vector. So it's always R crossed with F. So we write out our matrix of I, J, Ks. So we list the R vector first, so that's negative 3 in the X, 4 in the Y, and 0 in the K. And then for the F, there's nothing in the X, nothing in the Y, and just 6 in the K. Okay, so let's start with the I component. We're going to cross multiply, so that would be 4 times 6, and then 0 times 0. When we do the J component, it's negative 3 times 6, and 0 times 0. And when we do the K component, it's 3 times 0, and 4 times 0. Okay, so we cross these, we get 24 I hat plus 18 J hat. And since everything cancels away in the Z direction, our resulting torque vector is 24 I hat plus 18 J hat. Okay, now you could take this a step further too, because now that we know the vector, we can calculate the magnitude of that vector by doing magnitude in typical way. It would be the Pythagorean theorem. Okay, and there's 3 components, but Pythagorean theorem works the same way. You would just do x squared plus y squared plus z squared, take the square root of all that, and that will tell you the magnitude of your vector. Now, there's also a way to see the cross product in a shorthand way. Okay, if I just take the magnitudes of each vector and multiply by the sine of the angle between them, that will tell me the magnitude of that resulting cross product. Now, if I want to know the vector, you'll see that I wrote this little unit vector n hat, and the n essentially represents a vector direction that's perpendicular to both a and b. Okay, so it could be an x, it could be a y, it could be anything as long as it's perpendicular to both of those vectors. So if I want to know the magnitude of the torque, I just have to do the magnitude of the radius times the magnitude of the force times the sine of the angle between them. Okay, and you'll notice that when we define torque, that's exactly how we defined it. It was the magnitude of the radius r times the force F, and then times the sine of the angle between them. So it just kind of shows that that expression also comes out of doing the vector notations for torque.